Hi, welcome to Coding Architecture 2. This video is a refresher on the basics of Python so that everyone is on the same page. I want to remind you that this course is based on a roadmap that we published together with the first semester of Coding Architecture called Becoming a Computational Designer, which somehow outlines the process and the things that you would be required to learn in order to master the computational design discipline. The roadmap is built around the notion that you are somewhat already familiar with Grasshopper. So it is built on the equivalences between how to do things in Grasshopper versus how to do the same things in Python in code. And this is highlighted in green for Grasshopper and in blue for Python in the diagram. The diagram, the roadmap begins with the execution model, which is in Grasshopper is from left to right, following through the wiring, and in Python code is from top to bottom, going line by line. And then once we go into the specific details of how each of these lines is executed, we have different building blocks of what we can put in these lines. We have we have non-executable blocks, which is like a scribble in Grasshopper or a comment in Python. And then we have everything else that is executable that can be split into either data or algorithms or like building blocks for algorithms. For data, we will see a bit more in detail, but we have single values or lists of values or multiple values. We have also mappings and other type of data types. And in terms of algorithms, we have a number of building blocks that will help encode algorithmic logic. We can start everything starts with a single value actually, and then we can take that value and combine it with some other value. To combine two values, we use an operator, for example, an arithmetic operator, like plus. If we say 1 plus 1, then we have two values, 1 and 1, and then and then an additional plus operator that will combine that into a new value. That is called an expression. The combination of values, operators, variables, function calls, all those things. This is an expression and it returns a value. In the case of 1 plus 1, it returns 2. And then we can take that resulting value and assign it using a statement, an assignment statement, into a variable, for example. We also have statements for controlling conditionals and repetition and a bunch of other things. And then we will collect all these different building blocks into the next bigger building block, which is we want to define an algorithm. And an algorithm will be defined as a sequence of these things. Um, an algorithm is nothing more but a sequence of instructions that are solving a specific problem. And it can be a very simple algorithm, like the algorithm to calculate the absolute of a number, or a very complex algorithm. Once we have an algorithm, what we can do is wrap it into a function so that it can be reused. But we also have built-in functions in Python. So we can have like our own user-defined ones and the built-in ones. And the next level of abstraction would be, what if we need to put functions and the data that goes with it all together? Say, for example, that a function works only by analyzing a specific type, like points. Let's say a function that will calculate the average point or the centroid of a list of points. You will want to have probably that into a cohesive unit that is maybe like a class that will calculate um, taking as an input a list of points and will return the centroid. Let's say that we want to put it in a polygon class, for example. And the polygon class will take all the points, all the vertices that compose that polygon, and then it will want to calculate its centroid. You want to keep all the data together. You want to keep the list of points and the fact that you have a function that will calculate the centroid of this list in one cohesive unit. And that's a class, which we will see a bit more in detail in a bit. This concept is called object-oriented programming, and you will notice actually that in Python, everything is an object. So even though you will not be, I mean, we didn't define new classes until half or some, like, until a bit advanced in the first semester. We were using classes from day zero because they already exist in Python, in the built-in types. Everything is a class. So whenever you create something, you create even a string, and that is an instance of a string class that it's built in. Okay, but if we like zoom out, what we are basing on is this very high level definition of what software programs are. And this is a definition by Niklas Wirth, who defined software programs as the combination of data structures and algorithms. For our purposes, we're basically going to say that data structures are containers for data, and algorithms are instructions that are executed in a specific sequence. This definition is very close to um, an even simpler definition that is input, process, and output, in which process is the algorithm and input is data and output is also data. Input would be the data that is required for the algorithm to work, and the algorithm will modify that data and will create new data that will output. So let's jump into the anatomy of Python code. So this is an example of Python code that has a few of the building blocks that I've been mentioning. At the beginning, in the top, we have a few comments. Everything that is after a hash symbol is non-executable. It's a comment. And then in this first line of actual Python code that the interpreter will run, we have a value. This value is of type integer, so it's just the number 42. We're not doing anything with it, so it just is, but we're not doing anything, so it's lost after this line is executed. The next line is an expression, as I mentioned before. Here we have a multiplication operator that is multiplying 10 times 30. Again, we're not doing anything with that, with the result of this expression. So the value is lost. If we don't want to lose the value, we can assign the value that is the result of an expression. We can assign that to a variable. A variable is basically giving a name to a value. In this case, we would give a name to a fix, like a static value, 42. So answer will be, the variable answer will be equals to 42. We can also use variables in expressions. So in this case, we can say answer times 10. That will generate a new value. This is an expression. Expressions always create new values. But we're not doing anything with this result because we're not assigning it to anything. So we're losing it. We're fixing this in the next line by saying result, the result variable, equals answer times 10. And this is a statement. This is specifically, this is an assignment statement that will assign the value on the right to the variable on the left. Another type of statement that we have is a conditional statement, which starts with the if keyword, and it's followed by an expression that should evaluate to either true or false. So in this case, we are using a comparison operator, greater than, and we're saying if result is greater than 20, then this will be true, and we will enter and execute whatever is inside the if. Inside the if is defined as everything that is indented inwards to the right of that if keyword or line. Python uses this indentation principle to group things into blocks. So everything that is indented inside something, it belongs to the block of that statement. The same thing happens with the control flow statement for a for loop in this case. The for loop will repeat whatever is indented inside a number of times equals to the items that are in the thing that you're iterating over. In this case, we're iterating over the result of the function range, which is a built-in function of Python that will simply create a list of n items, in this case, a list of 5 items. So we will iterate 5 times, and we will print the result of all the items, because we will get them one by one assigned to the I variable, and those will be printed. So if we go to more detail, we need to see exactly how we define data. We will see first how we define data, and then we will see how we define algorithms. For data, we have 2 fundamental categories of data that we can define. Either it can be single values, individual elements, like 42, for example, is an integer, or 3.14 is a float, a floating point, a decimal number. Another built-in type is a Boolean, which is typed as bool, and it can be either true or false. In both cases, the first letter is capital. And another built-in type is string. A string is a sequence of letters to form a text. It's quoted with double quotes. Technically, it's possible to use single quotes, but for consistency, we use double quotes all the time. And then the next category is values that are more than one in one variable. So in this case, the variable values holds a list of integers. It's a list of 5 elements, and it goes in order 1, 2, 3, 4, 5. The square brackets are the identifying symbol for lists. This is a list created explicitly. We can also create computed lists, like for example, the range function creates a list, in this case, a list of 6 elements. It's similar. We can also create lists in different ways. We will see in a minute. We might also want to define geometric types, but Python doesn't have any. For that reason, we use Compass, the library Compass, for all the geometry types. And then we have all the usual suspects, points and boxes and vectors and this and that The definition of these types or creating one of these types looks more or less like this. We have the variable name equals to the type that we're creating. You will notice that all these types are capitalized, the first letter. That is a sign that this is a class, actually. So class point is a class, and we're creating a new instance of it, and we're just passing the x, y, and z um, values, coordinates of the point. Box is the same, well, it has three parameters. Um, different types will have different parameters. Okay, back to the lists. We saw that we can create explicitly a list of values. We can also compute a list of values. We can also um, create an empty list, for example. In this case, values equals an empty list. And then we can append values to that list. So in here, we will iterate um, um, in the range of 6, so 0, 1, 2, 3, 4, 5. And then every time we will append the power of 2 to that list. So this is the operator for power of, and that means that we are appending 2 to the power of I, and I will be 0, 1, 2, 3, 4, and 5, because we have 6 items in the range. This is a very relevant thing. So append in here, it's a function that is attached to a list. We create an instance of a list. This is effectively, this is an object which is an instance of a class. The class is list, is built in into Python. And it has functions attached to it. To access functions attached to an instance, to an object, we use this dot notation. That means that we take the instance of our class, our object. This is an important terminology. I will repeat it later, but a class is the blueprint of an object, and then whenever we create an instance of it, we call that object. So we have this object here, which is of type list, and it has a function called append, and that will append to that instance, right? This is different to like a built-in function that has no connection to any class, like range. Range is a function, it's built in, but it doesn't have any class attached. So there's no dot before it. It's just like free floating function. We will see a bit later that functions that belong to a class, we call them methods. This is the terminology. In this case, to be very precise, this is the append method of the list class. But we also have things like len, which is len is a built-in function, not a method. It's not attached to list, but it can work on a list. So we can say len of this list that we created here, and we can print that, and that will return the length of that list or whatever we pass that it's enumerable to len. Again, please note the lack of a dot before len. So we don't do values dot len, although it might be logical to think that it could be possible to do that. Python doesn't have a dot len function attached to lists. Sorted is also a very fundamental function that it's built in. It's not attached to list. It can take any sort of enumerable, and it will sort it. So if we have a list of values, we can call sorted of values, and it will return something that we have in order. Um, the reason why we are wrapping it again in a list is because in Python 3 in particular, sorted will return something called a generator. It's like a lazy way of doing something. It's like it will not really sort it unless you actually want to go through all of the numbers. So it just gets ready to sort. For most of the like practical purposes, you will not notice any difference. So you might easily say for I in sorted values, and that will just work. But if we want to print it like this, we have to convert it to a list. We have to say like, okay, now I want the whole thing as a list. Like, don't be lazy. And with list, we can do all sort of things. We can get parts of it, which is called slicing. We can get indexes of it. We can assign parts of it. So if we have a list of values, we can get the first one by saying, by indexing or getting the index 0 of it. So this means this is something about Python and many other languages. The first item in a list, it's the index 0. It's not the index 1, it's the index 0. Nowadays, most languages have this behavior. That's the first element in any kind of lists or enumerable in most languages these days is 0 and not 1. Python also allows us to use reverse notation. So we can say -1. That means start counting from the back and give me the last one. So this will return 23. We can also get a slice of it. So we can say from 0 to 3, and that will give us the first 3. We can also say, give me the entire list except the first one. So we say, starting from 1, remember that this is 0. So starting from 1, give me, like when we say colon, everything else. We don't specify, so it's like everything else. And we can also say, give me every second one. Give me all the odd ones, right? So it will give me the number, the index 1, the index 3, the index 5, and so on. And then like to kind of wrap up on these types, remember what I mentioned at some point in the previous semester, sorting is the mother of all algorithms. There's a lot of things that just are done by sorting the data first and then doing it. For example, Python has these built-in functions for calculating min and max of a list. So you can have values, and you can say print min of values and print max of values, and that will print the 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 the, the minimum and maximum of each. And you can also sort it, as we saw before. But alternatively, if you don't have a min and max implementation, you can always sort the values and then get the first and the last, and those will be the min and the max. This is not just to say, it's not just a simple like alternative. Sorting is used to all kinds of simplifications of algorithms. If you need to, if you sort your data first, you can make a lot of assumptions on how you work with it, and everything gets easier. So that's why like sorting is the mother of all algorithms. Okay, let's go to algorithms. How do we define them? Now we go back to the very beginning, like what's the most fundamental things of how to define algorithms. I'll reiterate, we have these like three main types of statements in algorithms. One is we could just define a sequence, like multiple lines, one by one, nothing special about them. They just execute one after the other. We have conditionals, which we have seen with the if statement. But if also has elif for if the first one did not match, then can we go to the second conditional, and else for everything that did not match any of the previous ones. And we have also loops. In this class, we're basically just focusing on for loops. There's another type of loop that is a while loop that is infinite until a condition is matched. But because of the execution model of Grasshopper and the fact that it's very easy to freeze it if you don't match the exit condition, then it's like less than ideal. Okay, so a bit more in detail, a sequence, it's kind of straightforward, multiple lines. If we want to print 1, 2, 3, 4, we have 4 lines, print 1, print 2, print 3, print 4. Conditionals, same thing that we saw before, now a bit more in detail. It's like a flow chart. We will say if certain condition is true, then it will go in and it will print whatever, like it will do whatever it's indented inside this condition, and then it will leave. It will go here. If the value would be negative, in this case, it would check this condition. It would not be true, so it would skip, would go to this line. It would be negative, it would print this, and it would go out. And if the value would be 0, exactly 0, then it will check this condition, not match it, go to the next elif, also not match it, and then it will say, okay, else. This nothing match, I can go into the else, and it will print this. Then we have the for statements, the loop statements, which I mentioned already. We can say for, and then we assign a variable name. This is up to us. We can name this anything. If we are iterating over a range, which is a very typical operation, we can use this like single letter variable like I or J, especially, or if we do iteration over X, Y, Z coordinates, we might call this X, Y, and Z. Other than that, if you're iterating over actual objects, it's much better to have a full variable name, like for item in list of items, for example. This would be the only case in which a single letter variable is okay. So to expand on this one, the range 5 function will create a list of these 5 elements starting with 0. And that means that I will be, the variable I will be assigned to each of them in a sequence, and then the content of the for loop will be executed with that value. So it will be print 0, 1, 2, 3, 4, with I being 0, then with I being 1, which is like more precisely, it's like saying I will be 0, and then we print I. I will be 1, and then we print I, and so on and so forth. Now, we have these like super basic building blocks, and now we want to do something a bit um, more useful. We have seen that these built-in functions like len, max, min, but we can also define our own functions. To do that, we use the def keyword, and then we give the function a name, and in parentheses we add the input parameters. And then we add a colon, a colon, and then indented inside, it's a sequence of instructions, anything of what we've seen already before. But at some point, if we want this function to return something, we need to say return and the value that we return. So here we see a very clear parallel between input, process, output. We have input being the input arguments for this function, which is a variable called number. In this case, we will assign it to 2 first and then to 3. Then we have the process, which is our algorithm. And we have a return value, either true or false, depending on what happens inside. And this is our output. So we have input, process, output. And now for the execution model, for what happens when we actually run this code. When we run a script that contains this, the first line that is executed is actually this one. So nothing in the function is executed initially. So we call print is even of 2. That means that the next line that will be executed is this one. So it's the function signature, the starting point of the function. And then the next line is this. So if number modulo 2 equals 0, that means if it's an even number, right? Modulo is their reminder of the division. So if the remainder of dividing over 2 is 0, it means this is an even number, and we can go here and return true. And after that, we will jump out, and that will print true. So we don't even touch these lines. So now we are back here. We go to the next line, 5. We're calling this function one more time, this time with the 3. That goes all the way back to the line, to the execution item 6. And here we have assigned number to 3 because this is here. So we go in this conditional statement and we will say if 3 modulo 2 equals 0. That's not true because 3 divided by 2 will return 1, the reminder. So it goes into the else statement and then it goes into return false. That means that it will go here, print return false, and continue or finish the execution. And by wrapping it inside a little function, what we manage is to basically make it reusable, because now we don't need to copy paste this in multiple places. If we want to recalculate this thing, we can just call isEven from anywhere that has access to this function. And then the next level of abstraction is, what if we want to combine data, like the data types that we have been seeing, and behavior into one cohesive unit? This is what object-oriented programming is, and it's very useful. It's a way of defining our own data types, right? It's a composite data type that also contains its behavior. So what is object-oriented programming again? There's two main terms that we need to remember. One is that of classes, and the other one is objects. So a class is a blueprint of an object. It's like a yeah, like a plan on how to create a new object. So if you have for example, it will define what are the attributes that this type uh, of objects collectively will have. For example, if you have rooms, as we saw kind of very briefly in the previous slide, if you have a class for rooms, the rooms might have a color, and that is what you define with the class. You say, I have a room, and all of my rooms will have a color. And all of my rooms might also have some behavior, like painting them. So those will be functions inside this class. So the class defines this blueprint, and every time that we want to create one specific instance of it, we're creating an object. So we say, I will create my room. So my bedroom is an instance of the classroom, and it has specific values. It's white, and it has these dimensions, and it is one specific instance of it. So let's go to the more in detail the anatomy of a class. The class definition starts with the class keyword, and it's followed by the by the name of the class, which is by convention it should start with a capital letter, not contain any underscores, and every new word in the name of the class should be capitalized. So if we say that we have a class um, for example, uh, kitchen appliances, then we will say class kitchen appliance in and K and A, the first two letters of the first two words of the two words will be capitalized. There will be no underscores, just the two words combined with the first letter in capital. Then we need to tell it what is the object that we inherit from. Um, there's always one object that we inherit from, even if we don't inherit from anything, because everything in Python is an object. This is what explicitly or implicitly happens. We say room is actually an object. We can also inherit from other things. We will see inheritance a bit later on. What is important maybe to highlight here is that in Python 3, this definition of everything it's an object is not necessary. So you can have class, room, colon, and that is valid Python 3 code. So that's the starting point, and then everything inside, so everything that is indented inside, it's the content of the class. And we have on one hand behavior, so we can have a function defined inside a class. A function, when it's defined inside a class, it's called a method, as I mentioned before. It has exactly the same structure as a normal function, with the only difference that the first argument will be called self, and it refers to the object on which this function is being called. So if I take again the example of my room, I created an instance of my room, which is my bedroom, which has the color white, and that means that self.color will equal to white. And if I call the paint function and I change that, then the self color of my room will change to new color. This would be like a very trivial uh, creation of behavior that is attached to this class. And we also want to attach data to it. This usually is done by creating attributes into the class. An attribute is basically a variable that is glued, attached to an instance of an object. We normally do this in the init, which is a special method that is the initialization method. It's the first thing that happens when we create an instance of a class. So in this case, what we're saying is to create a new instance of a room, we want to have a name, a height, and a color. And these inputs we will assign as attributes of the object. So we will do this self.name equals the name, the input parameter name, self.height equals the height input parameter, and self.color will equal the color input parameter. Notice that the name of these variables or input parameters are matching this, but that's not necessary. It is by convention what usually happens, but it is not necessary that they match. Okay, and now we have created we have everything to combine data and behavior. And what we can do is, what we end up with is um, this element, this item, this class, which is the blueprint on how to create rooms. It has these attributes, 3 attributes. It has this method, paint. And we can start creating new instances of it. So we can say my room equals room for these values. and it will have the paint method as well attached, but it will have the data for my room. I can do the same thing with the kids' rooms and assign, again, variables to it, like values to it. And then I will have two different containers that have, each of them have data, and I can call paint on them, and they will refer to themselves. So if I call paint on the kids' room, it will not be mixed with my room. So I will not accidentally end up with coloring another room by mistake. So wrapping up, and in terms of object-oriented programming, OOP, the building blocks, let's say, of OOP is there are the constructors, which is this special method called double underscore init double underscore. So when we say my room equals room, for example, we are actually calling this constructor. These methods that have double underscores before and after, they are called dunder methods in Python. Dunder because double underscore. Very creative. So this is the constructor of the class. Then we have attributes, which is if we assign a variable to the instance of self, right? Or if we assign it to the instance name, that is an attribute, that's a variable that is attached to that instance. So if we say red equals the color of my room, then when I do a color equals my room dot color, I will be putting red in here. Or if I say print my room color, it will print red. Notice that here red, blue, these things don't actually exist in Python. So you don't have something that is a keyword red that will really be red. This is only an example. To represent colors, you need a library that has the concept of colors. We are going to use Compass for this. So we will use the color class of Compass in general. So we have, back to the building blocks, we have attributes, we have methods. Methods is a function that is attached to it. So if we want to paint a specific room, we can do my room dot, the dot notation, paint with the new color. And we have something that we didn't see explicitly, but some methods are magic. They're called magic methods. For example, this dunder str string. If you add a method that is called like that and you return a string from inside the method, whenever you say print my room, for example, without any details, it will call this function and then get the string that represents this thing and print it. It's useful to avoid the very ugly default behavior when you print an object that will say something like class name and then a memory address or something very unfriendly. Okay, that's kind of it for a Python refresher. One very important thing to highlight is in this semester we're moving away from Rhino 7 and Iron Python 2.7, and we're going to use Rhino 8 with Python 3, CPython effectively, and it's Python 3.9 to be very precise. That has a few very positive um, consequences. But I want to also highlight a few of the differences so that you like figure out what the if you get syntax errors, you know what they are, because some things have changed. For example, the print function. This is one of the biggest and silliest changes. In Python 2, you were able to say print and then whatever without parentheses, and that works. In Python 3, that doesn't work. You need the parentheses. This is because print now is a function, and functions always need parentheses. Range also changed behavior. So in Python 2, you could say print range of 5, and it will print all of them. If you do the same thing in Python 3, it will not print all the numbers. It will print the text range 5, because this is a lazy range. It means it's not really going to expand until you force it to expand. You can force it to expand by wrapping it into a list, for example. The same is something very similar is true for things like iteration over keys and stuff like this. If you have a dictionary like this, if you have a dictionary like this, in Python 2, this would actually print out the keys of that dictionary, but in Python 3, this will not. This will return an iterator, and to force it to expand, you need to say list of this. Now, this one is one of the biggest changes and most relevant for improving your performance as a coder. Python 3 adds typing information. Typing is a very big topic. I will dig into this with more details during the semester, so don't worry. But you will see this additional syntax. Some things like input, arguments, and also return values, they can be declared as what are the types that they are returning. So when you have, before we would have written def, average, numbers, we close parentheses, and then we have the final colon. In Python 3.9, we can say numbers is going to, needs to be a list of floats, and this function will return a float in the end. So then we do whatever we do, and then this results into a single float because we're calculating the average of a list of numbers, and this matches. This is very helpful for autocomplete, and you will get much better results with typing on, basically. But it is completely optional. You can skip the typing information whenever you declare something new. And finally, string formatting. This is also relevant. In coding architecture 1, we used a lot of this. We were having a string and it had these curly braces in between that were empty. And at the end, we would use the format function of the string class, and we would pass all the variables that would be like injected into this. And this would be in positional order, right? So if we had 3 of these sets of opening and closing curly brackets, there would be 3 variables here, and they would be like positionally injected. In Python 3, we have something called f strings, which is a string that is prefixed with this f in here. And instead of doing all this whatevering with format, you can say curly braces, and inside the curly brace, you can just type a bit of Python code. Ideally, just a variable name, but you can also add an expression. You can say 1 plus answer, like, or anything actually works. This makes it like a big difference in readability for when you're concatenating or creating a longer string with data. Okay, that is it. I hope you enjoy this. I hope things are clear, and see you very soon in class. Bye bye.